to everybody. Today we have Carlo Gasparetto. He's a student of Professor Guido De Filippis. And the title of his talk is "You Can't Always Touch a Minimal Surface." So please, Carlo, you can start.
Thank you, Sarah, and thank you, everybody, for being here. Today, I'm not gonna talk about my research in particular. I'm going to talk with you about some features of minimal surfaces that I also used in my research, but in order to get not too technical, I'm just going to stay focused on a larger picture, maybe less technical. So the basics. A minimal surface is just let's say, an n-dimensional smooth submanifold of RD, for which we require that its mean curvature, which is the sum of its n principal curvatures, vanishes at every point. Okay, you can think of a plane, of a catenoid, or a couple of planes that is a perfectly admissible smooth submanifold with zero mean curvature. The mean curvature itself somehow resembles a Laplacian in this sense. If you assume that sigma is the graph of a smooth function, which you can always do locally, at least if u is smooth, if sigma is smooth, we can also reduce ourselves to the case where the gradient of u in the origin is 0. Sigma passes by the origin. And in that case, the mean curvature is just the Laplacian of u. And stating that the mean curvature is 0, in particular, implies that the Laplacian of u at a point where its gradient is 0 is also 0. So in some sense, the Laplacian is, I mean, not in some sense, the Laplacian is actually the linearization of the mean curvature, in the sense that for small gradients, stating that the mean curvature is 0 amounts to saying that u satisfies some elliptic equation of this form, where A is a matrix which is close to the identity. Okay, now I'm going to go back to the title of my talk, why you can't always touch a minimal surface. To see this, we should go back to functions and see how can I touch the graph of a harmonic function. Harmonic functions are the function equivalent of minimal surfaces. And if I want to have a function that touches the graph of u from below, say, then at the point of contact, the Laplacian of the touching function must be negative. Vice versa, if phi touches u from above, then at the contact point, the Laplacian must be non-negative. Vice versa, if a function is continuous and is such that both these conditions are satisfied, that is, every time I touch it from below at the contact point, my Laplacian is non-positive. Every time I touch it from above at the contact point, the Laplacian is non-negative. Then actually, I can prove that u is not only continuous but smooth, and it is in fact harmonic in the classical sense. A continuous function which satisfies these two touching conditions is said to be a viscosity solution of the Laplace equation. Proving regularity for viscosity solution is kind of reasonable in the case of the Laplacian. It's more involved in the case of general elliptic operators. And well, it's part of what I'm going to tell you about minimal surfaces. Now, let's translate back this viscosity approach to minimal surface. This amounts to stating a maximum principle for minimal surfaces. That is, say I have a minimal surface, let's say a codimension 1 minimal surface, that is a d-1 dimensional surface. What condition must satisfy a smooth function that touches this minimal surface? Well, say that my this is my minimal surface, and say that I have a smooth surface touching at the point 0 my surface. Say this surface is the interface between the positivity set of a function f and the negativity set of a function f. Assume also that the gradient of f at that contact point is a vector, a unit vector, say ed. Then, if I linearize both the test surface that f equals 0 and the minimal surface around 0, what I obtain is that, okay, say that the interface is the graph of some function phi, sigma is the graph of some function mu. Sigma is minimal, therefore its gradient, the Laplacian of u at 0 must be 0, as we saw earlier. But this implies that also the Laplacian of phi must have a sign. Now it depends on where I'm looking, if I'm looking like this or like this, but let's say Laplacian of u of phi is positive. So let's say phi is touching u from above at 0. And if I translate it back to f, the testing function, this amounts to saying that when I take the Hessian of f at 0 and I test it against unit vectors that are orthogonal to the gradient of f, this trace, this is some kind of trace of the Hessian, must be non-positive. Okay. So to the thing for a second. I'm looking at my function like that. Phi is the graph, is the function whose graph is touching u from above. Its Laplacian must be non-negative. Therefore, I can say this inequality on f, on the Hessian of f. In dimension, in general dimension, if sigma is n-dimensional surface, then I won't be able to control d minus 1 directions, like in this case. I will only be able to control m eigenvalues of the Hessian. So again, if sigma is an n-dimensional smooth minimal surface and the positivity set of f is touching sigma at some point, like in the previous drawing, then something like this must happen. I can find n orthogonal unit vectors so that this kind of trace is non-positive. Okay. In short, we can say that there is a plane, n plane S, such that its orthogonal, its scalar product with the Hessian is less than 0. By the way, the scalar product is just Sij di dj f computed as 0. It's just the Hilbert-Schmidt scalar product. What I'm saying is that the trace of the Hessian is non-positive when projected to on the plane S. And also I can say that S is orthogonal to the gradient of f. Okay. Having this in mind, we can try to generalize it. We can try to weaken the definition of a minimal surface and say that a minimal surface is any surface, any closed set actually, that satisfies this kind of touching condition. Every time a function touches it, the positivity set of a function touches the set, it must satisfy an inequality like this. So we introduced this definition of MH set, which was invented by Brian White, which should resemble an n-dimensional surface with a curvature that is bounded by h. That is, when I take the parameter h to be 0, I'm just looking at n-dimensional minimal surface that are with curvature 0. So take a closed set and assume that f restricted to sigma as a local maximum at P. What does it mean? It means that this is sigma, this is the positivity set of F, and sigma all lies in the set F less than 0. So when I restrict F to sigma, here is all negative, here it is 0. Okay? Then F must satisfy this, this condition. Again, if it confuses you, just think about the case H equals 0. Then I'm saying just the maximum principle I stated earlier. And I say that a set sigma that satisfies this condition for every touch in function f is a MH set. Okay. Let's do something easy for getting used to this MH set. Let's prove that if sigma is a MH set, then its diameter must be larger than some constant over h. This is reasonable. If you take h equals 0, you are just saying that a minimal surface, a M0 set, cannot be compact. It cannot be included in a ball. Makes sense, right? And how do we prove it? Let's do it by compactness, by contradiction. Say that you have a MH set sigma, and say that it's actually bounded by a ball. Well, then this ball, there must be a ball that touches sigma at some point in its boundary, which amounts to saying that the function u of x equals absolute value of x as a maximum at that point. But if it has a maximum at that point, I use the fact that sigma is a MH set. And so it must be that S scalar product, the Hessian of F at that contact point, is controlled by h times the modulus of the gradient of F. Okay, but the right-hand side is just h, and the left-hand side, just some easy computation. If I do the Hessian of the modulus, I obtain that it's something like that. And this implies that actually the radius must be greater than n-1 over h. Okay, so minimal surfaces are not compact. Perfect. There were like 100 easier ways to prove this, other than introduce MH sets. Let's do something a bit more technical maybe now. Let's say that actually MH sets include minimal surface. And to do this, I'm going to use the notion of integral varifold. So if you followed Luigi De Masi's AJS, you should be kind of used to varifolds. Let's say for our purpose, it's just a measure M, which is just a Hausdorff measure restricted to some say smooth n-dimensional surface E, but it can be also an M-rectifiable set times an integer valued function. Okay, these are not all the possible variables, but are the ones I'm interested in. And I can state a notion of minimality, a notion of stationarity for these variables, which amounts to saying that they have zero mean curvature. And well, it goes like this. I just take a test vector field y, and I move m by pushing it with this test vector field. When I move it, the mass of the measure, like the total mass of the measure, varies by these amounts at the first order. And what I can say is that if this quantity is bounded by h times the L1 norm of the vector field, then actually M is in some sense a manifold with bounded mean curvature. I mean, in the smooth case, if E was actually a smooth manifold and theta was a constant, saying this would equate to saying that E is a manifold with a bounded mean curvature. Of course, if I take the parameter h to be 0, I only obtain minimal surface. And in the language of varifolds, I'm talking about stationary varifolds. Okay? And well, we can prove that stationary varifolds, that is varifolds for which this equality holds with 0 on the right-hand side, are actually M0 sets. To do this, we consider a stationary, okay, this is kind of a wrong title. It's not the varifold itself that is an M0 set. It's more the support of the varifold. So I take a stationary varifold, I take its support, sigma, and by contradiction, I assume that there is a function touching sigma at some point, for which the inequality fails. I recall the inequality was for all s, no, sorry, there exists one s orthogonal to the gradient of f in 0, such that s scalar product, the action of f, is negative. Okay, let's say this isn't true. If this isn't true, then what I'm saying is that for every s, and for every point in a small ball around the origin, this inequality fails by something, by delta, okay? This is just the negation of this. Okay, but if this is true, I first remark that outside this ball, my assumption was that f had a maximum at 0, when restricted to sigma. Well, then, outside this ball, the supremum of f on sigma must be less than the value of f in the point 0. And without loss of generality, I can assume that I can put the 0 set in there. So I have the interface f equals 0, the interface f equals f of 0, and this set f greater than f of 0 stay all on the right of sigma. Okay, and now I take a test function y. I take this f times the gradient of f. So it vanishes on this interface, and it points everywhere as the gradient of f does. And I also restrict it to the set where f is positive. So I'm only moving m inside the ball. I'm moving sigma inside the ball. Recall that testing m means moving the varifold with the test plan. This test plan only takes values here. So I'm moving m inside here, and I can write what the first variation is. This is the quantity I want to estimate. So this quantity has to be 0 because I'm in stationary, okay? And for a stationary varifold, this quantity, the first variation, is 0. But this quantity on the other end is just, if I take this divergence, it's just S scalar product deviation. And this has two components. One component is just f times the action of f. The other component is just s time df. I'll just write it, sorry. This is the first component. So when I do the scalar product with f, I'm just doing f times the scalar product between this and s. And then I have another component, which is df tensor product df. And when I do the scalar product with s, the second component gives me this scalar product. Now, S is an orthogonal projection on an n-plane. So this scalar product is positive. I mean, the linear form is positive definite, and this scalar product is positive. So this is just greater than the first summand. But the first summand, recall that I was negating this sentence. So the first summand is just greater than delta times f. Okay, so the quantity above is just greater than delta, the integral of f, and okay, this is obviously greater than 0. On the other hand, we said by stationarity, the same quantity must be equal to 0, and I reach a contradiction. So what I proved is that the support of a stationary manifold is indeed a M0 set. Okay. Hoping that things are kind of reasonable until now, I'm going to talk about a more a result which is a bit more technical, and I hope I'm not reducing you all. I'm going to state some useful, some kind of interesting application of the MH set, which is proving some regularity for minimal surfaces. What we want to prove is a Allard type theorem. That is a theorem stating that if I have a minimal surface, like a stationary manifold, and this stationary manifold is close enough in a suitable sense to a unit density plane, then actually this surface is smooth all the way. What does it mean? Take a catenoid. If I look around here, my catenoid is not too far from a plane. That means that around this point, I can say, okay, I'm actually smooth near that point. And I can say something like that for M0 sets as well. Actually, for MH sets is fine enough. But I'm going to focus on the case in which M, the dimension, is D minus 1. So I'm looking at D minus 1 surfaces. You can think of graphs, okay? And the curvature is 0. So I'm stationary and not just with bounded in curvature. I assume that that I'm close enough to a plane. What do I mean by close enough to a plane? I mean, let's assume that the point 0 is in the set, that the measure of the set does not exceed too much the measure of a disk. And this is just saying that if I have sigma, I take a ball of radius 1, I measure what's inside here, and I'm not going too much over the measure of a disk, of a single disk. This is to prevent something, some double sheet behavior. I may have the surfaces, like I said, two planes, one above the other. Well, if I look in a ball large enough, I'm not going to be able to say that it is a graph in that ball. Okay. And the last thing, the real closeness to the plane is this. I'm saying that again, if I look in a small ball, in a ball of radius 1, I can fit my my D minus 1 0 set in a strip. In a strip small enough, a strip of width epsilon. If these conditions hold, then, and epsilon is small enough, then I can actually say that in a smaller ball, in a ball of radius 1/2, sigma is actually a C1 alpha graph. As you know, after C1 alpha, I mean, it's just a matter of elliptic irregularity, bootstrap argument, and stuff like that. And you obtain that sigma will be actually C infinity. How do I prove this, and what does it have to do with MH sets? I mean, why do I have to use this kind of viscosity definition of minimal surface? The point is this. I want to prove a improvement of flatness result. This is the core of the thing. Let's say sigma satisfies all of the hypotheses I said earlier. So I'm epsilon small. I want to prove that in a very much smaller ball, in B eta, if I tilt a bit the system of coordinates, then I am much flatter. Notice that here I'm requiring that the flatness is epsilon, the width of the strip, divided by the radius of the ball, which is epsilon. On the other hand, here I'm requiring that sigma lies in a strip of width eta times epsilon halves, but it's in a ball of radius eta. So I'm halving actually the flatness. The situation is this. I have my surface, it's included in a strip of width epsilon. At a smaller scale in b eta, I can tilt a bit my system of coordinates, and I will be in a strip which is much smaller than epsilon. Okay. And also, I want to stress the fact that tilting the system of coordinates is essential. It might happen that sigma is just a plane, which is, of course, d minus 1, 0 set. It's a minimal surface, a smooth one. But if I don't twist the coordinates, then I'm not going to be able to gain some flatness. It will always stay epsilon flat. Makes sense? I have to tilt the coordinates to accommodate for the fact that sigma might turn a bit, or it can just be tilted. Okay. Why this improvement of flatness, this epsilon at scale 1 implies epsilon halves at scale eta work? Why does it give C1 alpha regularity? Well, it's because after I do it once, I can repeat. I can iterate. And I can obtain that at scale eta to the k, it's epsilon divided by 2 to the k flat. Okay, to state it more clearly, this is the relation I have. I can find some vector, nu, which is kind of the right normal to the graph, so that this kind of decay holds. Inside a ball of radius rho around the origin, sigma is included in this strip. So if this is 0, let's say this is nu, and I will have that sigma must be inside this kind of strip. Okay, and this, okay, if you do it for many points and you compare the things between them, you will eventually end up with saying that sigma is a C1 alpha graph. This is the core of the thing. Now, how do we prove the improvement of flatness? This is going to be kind of a proof by drawing. Say, okay, it's we prove it by contradiction. Say that I have flatter and flatter surfaces, so that they stay in a strip of width epsilon j, with epsilon j going to 0. I stretch them in the vertical direction, like this. I have the surface and I just stretch it vertically to obtain this. And then I have a closed subset. These stretched surfaces are just closed subsets of a strip of width 1, this minus 1, 1. So they converge, at least in a Hausdorff sense and up to subsequences, to some other closed subsets. The tricky part is to prove that they converge to a graph of a function. But once you have that, you are done, because you can prove that U, the function whose graph they converge to, must be a viscosity solution to the Laplacian of U. Okay, and being the viscosity solution to the Laplacian of U, well, U must be C1 alpha. My surfaces are close to the graph of a C1 alpha function, so they must have this improvement of flatness property. Okay, to do so, I proceed like this. Let's say this is my surface. There is scale 1, so it's between -1 and 1. eventually these surfaces tend in the Hausdorff distance to a graph, this red graph U. I want to prove that U is a viscosity solution, so what do? I touch it from below, or from above, let's say from below, with a function. From below with a function, and I want to prove that this function satisfies the right inequality, which is the Laplacian of this function at the contact point must be non-positive. Well, if this function touches U from below, then some translation of it must also touch the surface that was going to U. Okay? Nice, but now I have a function touching sigma tilde j. If I go back to the original coordinates, like I rescale in the ED direction again, I have a function fj, which has a touching condition like this. Its positivity set is touching my minimal surface. It's positive under the surface, it's negative all along the surface. Therefore, f restricted to sigma as a maximum at some point. And in particular, we can state the usual inequality for the Hessian of f. Okay, but now it's kind of just computations to go back from this formulation to the one for phi, obtain this. Notice that the left-hand side of this equation is just the mean curvature of the graph of epsilon phi. So what I'm saying is that the rescaling of phi has negative mean curvature. It's kind of what we were expecting because phi was touching a minimal surface from below. Must be that I can say something about its mean curvature at the contact point. Okay, but now I have this quantity, I can send epsilon to 0. And I obtain that the Laplacian of phi at the contact point, the original contact point, is non-positive, which is what I wanted to prove. So U, the function that was touched by phi, is harmonic, because I can do this for every point and also from above. So U is harmonic. Therefore, it has some C1 alpha estimates, but also sigma was close to the graph of U. So it also must have the improvement of flatness. And this should kind of conclude the proof of the Euler theorem. And from the improvement of flatness, I get the C1 alpha. This is actually the end of my talk. I'm sure I'm sorry I wasn't too clear. It's I mean the Euler theorem was a bit technical, but I hope I told you something about maximum principle for minimal surface and how to use it.
Are there any questions?
Hello, one. During your talk, you proved that a stationary variable is an M0 set.
Yes.
What about the converse? So, an M0 set induced in some sense a stationary variable?
Well, yes and no. Okay, let's say this. If you know that you are in the hypothesis of the Euler theorem, then your M0 set is also smooth. Yeah. And in particular, of course, it induces a stationary variable. But that's not always the case because, say, it's okay. Say that this plane is obviously a M0 set. Okay, because whenever you touch it with a function, the function must have, I mean, it must be curved in the right way. But now if I fill this part of the plane, this also stays a M0 set. So in some sense, yes. In some other sense, you can't expect all the regularity you have for all the regularity you want. It might be that an MH set is, for example, it may have infinite n-dimensional house of measure. Don't know if
there was wondering if there is some way to overcome this, but
I think you need some assumptions like the one of the epsilon variety. Maybe weaker than this, but you definitely need something.
If you assume that the set is rectifiable, then zero set is rectifiable.
Maybe you can, yeah. Maybe you can say that that if you give it density 1, then it is actually a unit density variable, a unit density stationary variable. I think. The point is that being rectifiable doesn't guarantee you that you can be touched in many points. You can be rectifiable but still be very wide, and I can only touch it with most function. I mean, I can touch it in too many points. Maybe I haven't looked into this.
And another question: when you stated talking about viscosity solution for the Laplacian, you told that a continuous viscosity solution of the Laplacian is harmonic.
Yes.
What about if the function is not continuous, some other pointwise property? That's a curiosity.
It's kind of natural to assume that whenever you are testing with functions that touch your graph from below, it's kind of natural to assume that your function is lower semi-continuous. Otherwise, you can't really touch it. I mean, there may be some points where the touching is not really happening. And when you say it's a viscosity solution, you mean it's both touched by below and from above. So it's natural to assume that a viscosity solution is also continuous.
Are there any other questions? Maybe there is one line. Ivan,
yes, hi. Yes, I have one question. The scale of the improvement of the flatness is explicit, or because because of the compactness argument? So it's just there exists some scale eta depending on the dimension, which is not explicit, or is it explicit in the end?
The proofs I know don't make it explicit. No. Actually, it's explicit. It's explicit.
Okay, computed. Okay.
Yes, it only depends on the regularity properties you have for the harmonic functions.
Ah, okay. Okay.
The epsilon, the thing is that line. If epsilon is small enough, this improvement of flatness holds if you choose epsilon small enough.
And that threshold is not explicit.
It's not explicit.
Okay, so that's the part where, okay. Okay, thanks.
You're welcome.
and is this C1 alpha the best you can get, or you can expect?
Yes, with only this argument, yes. If you don't have any bootstrap argument for later, that's
so are the results same mode or?
not that I know, no. I mean, I wouldn't know how to approach it to get more than C1 alpha regularity.
Are there any other questions? Okay, so we can thank Carlo again.